Okay, I want to solve an example problem here of a one sample hypothesis test. So we have this problem, American Water Works Association. They report that their per capita water use in a single family home is 69 gallons per day. Legacy Ranch is a relatively new housing development consisting of 100 homes. The builders installed more efficient water fixtures such as low flush toilets and subsequently conducted a survey of the residents. 36 homes responded to the survey, and the sample mean water per day was 64 gallons with a standard deviation of 8.8 gallons per day. At the 10% level of significance, is that enough evidence to conclude that the residents of Legacy Ranch use less water than the average? So let's go ahead and open up this starting file and start solving this problem. Okay, we see in the starting file we don't have much except for the question I just explained. Essentially, the thought process is this: read through the problem again and try to pick out some keywords and start documenting everything that's known. So let's go through this problem and document some things. So we have the American Water Works Association report that the capita usage in a single family home is 69 gallons per day. So we know we have this value, a value of 69. Let's go ahead and document that. The next thing that we have is 100. So we have 100 homes in this ranch development. Is basically the entire population. Okay, but we need to know the information more associated with the survey, which will be later described. The builders installed more efficient water fixtures such as the toilets. 36 homes responded to the survey. That is going to be our N, our sample size of 36. That's what we are investigating. We're investigating the results from the survey. Okay, that means that our degrees of freedom is going to be equal to 36 minus 1. Okay, so let's read on. 36 homes responded, and the sample mean water per day was 64 gallons. So let's document this as X bar. X bar was 64. And a standard deviation, we can write STD or SS for sample standard deviation of 8.8 gallons. And alpha is going to be 10%, 0.10. Okay, so that's about everything we know in the problem so far. Now, in terms of hypothesis testing, what we really are comparing is the sample information based on everything that we collected. The sample is everything under this value, and I know that's probably a little confusing. So if we separate out the information from basically the report, we're comparing the report to this ranch. So the value that we're comparing our sample to is this value of 69 gallons per day. The question we're trying to answer is, does the ranch use less water than this value of 69? So if we separate this, the information here is from the survey. That's where we have the sample size of the survey, the X bar, the survey result of how many gallons were actually used at the ranch homes that responded to the survey. We also have a sample standard deviation of 8.8 and so forth. So there is one keyword that we need to identify in order to conduct our analysis. And I recommend just going ahead and documenting this keyword. So when we read this, we have to determine if this one sample test is based on a direction. Are we testing, let's say, the left tail? Are we testing the right tail? Or is there a consideration where we have to test both tails simultaneously? In this problem, the keyword is less. So let me read this again. Is there enough evidence to conclude that the residents of Legacy use less water than the average value reported by American Water Works Association? That is precisely the test. So our keyword is less. Anytime there's a direction associated with a keyword, we're testing one tail or the other. We care that this ranch is less than the average. That's at least what we want to test. So with a keyword of less, that means we're going to be testing the left tail. So when I write my hypothesis statement, I have my H0 and my H1. Some call that HA. However you want to document that is fine. My null hypothesis is mu is greater than or equal to value. Now, if you're not that familiar with hypothesis testing, I don't even recommend going straight to the null hypothesis. I actually recommend doing something different. I recommend actually filling out the alternative first. So the alternative is what we have to base our analysis on, or at least to me, it makes the most sense. We're reporting that we want to compare our sample to a value of less than. So what we're actually doing is comparing 64 to 69, statistically, of course. So what we want to say is our sample mean, and I'll call that mu, is mu less than the value. Okay, that's really what we're testing here. And if it confuses anybody, I will replace x bar with mu, our average. 64, is our average less than the value reported by American Water Works Association? That is exactly. We would love to conclude that yes, in fact, the ranch uses less water. Once you have identified this correctly based on your keyword, then you just have to write the opposite statement. What I mean by that is mu and the opposite of the bottom alternative, less than, would be greater than. And we know that the null has to have an equal sign. That's the way to do it. Your null, your HO, will always have an equal sign. The alternative never does. So is this greater than value? So we need to see if there's enough evidence to conclude that yes, mu, our sample average, is less than, or I should say less than the value. Okay, I'm going to just provide a little format here quickly. Since this is a water problem, let's go with blue. And maybe, why not, white text. Okay, so we're at a point where we've documented everything we know. And we got to make up our minds if we're going to use a T test or a Z. Now, let's go ahead and open up our formula sheet. And let's go ahead and scroll down a little bit. And when we scroll through, what we want to find is this one sample hypothesis testing, the approach. So I definitely recommend reading through these notes that I've provided you and looking at the step process. So step 1, state the null first and alternative hypothesis. I actually recommend using the keyword and stating the alternative, then the null. Level of confidence, we have that at 10%. Identify the test statistic. That's what we're trying to do now. Is it a T or is it a Z? And essentially the difference is the Z, we have to be told that it's from the population. If it's from the sample, we're going to use the T. Formulate the decision rule. So we will do that based on our the way we wrote our statement. And basically step 5 here, take a sample, arrive at a decision. Basically what that is referring to is we've already got our sample actually. Do we reject or do we fail to reject the null hypothesis. Okay, so scrolling through here, just trying to pick out some more interesting facts, setting up the hypothesis. What I would do is look for those keywords. Those keywords in our case was, is it less than? So you can look through this table of an example that I've provided, and less than would be very similar to smaller or less, which is going to be this inequality symbol, which is a part of the alternative H1 hypothesis, which is exactly what we wrote. And if you need to visualize this, what I would recommend is actually looking here. It is a keyword of less than, a decrease, is it smaller than in other words, and simply just using what I've written here. Mu is less than value for the alternative, and the opposite is true for the null. It is greater than or equal to. So if you need to copy these things, you can actually click on these, copy image, and I've seen some students do this in the past, that they'll simply paste these notes right by their problem. So you can actually copy this too. The one-tailed, left-tailed test is exactly what we're doing in this problem. So let's go ahead and paste that information. So it's very clear what we're actually striving to solve. Okay, now we do in fact need to make a decision if we're using a Z or a T. Now I'll tell you, there's nothing in this problem that states that we know the population. In fact, we were told that the sample mean was 64 gallons. We weren't told it was the population mean. We were told that it was a sample mean. So we have to assume that we're going to use the T, because we weren't explicitly told that the population would mean that we had all the information through the 100 homes in this Legacy Ranch area of town. So we have the sample. We have the sample of that. We have 36 actual samples of the 100. So that's a sample by definition. So we're going to use the T. So we need to calculate the test statistic and the test critical value. So let's go ahead and document this. We need T stat and T critical. Okay, and it's going to mirror this. So we have our null and our alternative. We know where the rejection region lies. It lies to the left of the critical value. So this figure is just as presented as a guide, but it's useful when interpreting these values. So let's go ahead and calculate what the test stat would be. Let's go ahead and look at that formula sheet again. Here we see a table, one sample hypothesis testing, test statistics. Okay, we need this T value. We know it's a T, so we've already sort of went through this process already by eliminating all these Z. And let me show you how I would use this spreadsheet. Population standard deviation, this is the first question you've got to ask or answer to yourself. Were we told that the sample was from a population, or was a survey results from a sample? It's from a sample, so the answer is no. So we can ignore these first three rows. Okay, now we have three possible categories that we can choose from. Now, in the long run, it happens to be that T is calculated the same way everywhere, but I want to go through this process because all the rest of the tables should be interpreted this way. So once we have said no, we have eliminated the top three. We are now focused on the bottom three. Is the test direction testing both tails? No. So we have eliminated this. Is the test testing a direction of less or the left side? Absolutely. So we're testing one tail. We are in fact using a test statistic of a T, and we need to calculate the T stat. So the formula is x bar minus mu and x bar is our sample average from the survey, minus mu, which you have to keep these straight in your head. The mu is actually the value, and divided by the standard error. So let's go ahead and calculate that. So equals, parenthesis, we have the mu from the sample minus the mu of the reported value divided by the standard deviation, which is 8.8 divided by square root n, which is 36. Okay, so we get a test statistic of 3.4, which means you are very far away from the mean. 3.4 standard deviations away on the left-hand side, of course, because it's negative. Now all we have to do to make this decision is to calculate the t-critical. Okay, so how do we do that? Let's go back to this formula sheet. And on the next table we have one sample hypothesis testing the critical values. Okay, we go through a similar approach. Is the test using a z? No, so we can ignore all this. Is the test a t? Absolutely. So is it both? No, so we can ignore this row. Is it testing the left? Yes. So just to double check, here is our, here is our null and our alternative. And if we are going to calculate the critical value, we need this part of the formula, alpha and degrees of freedom. Unless otherwise explicitly stated, degrees of freedom is always n minus 1. Okay, so let's go ahead and copy this formula over, go back into our sheet, and I'm going to go ahead and paste this. T dot inverse alpha. Alpha is 0.1. Degrees of freedom was already calculated, n minus 1, 35, and hit enter. Our critical value is at 1.3. So essentially what this means, and I like to utilize paint when I can, because I think it's important to visualize what's really going on. We have this distribution that looks something like this, and we have a center. What we're doing is we're trying to find a specific region that looks like this, and this is where our t-critical lies, and that t-critical is equal to negative 1.3. Okay, now the rejection region is what I'm going to fill in here with black. So just imagine there's a straight line up from this t-critical value, and I know that's not straight, but this region is the do not reject. The do not reject. Okay, the do not reject region. If we're on this side, we are in the region of rejection. So region of rejection. Okay, so now we have to find out where this test stat lies. The test stat is -3. We determined that already. We know -3 is to the left of this -1.3, so I'm just going to arbitrarily draw it here, and this is where the test stat lies, and it's -3.4. So to determine which region you're actually in, it's all based on this test statistic, and you got to know where the critical area lies. The critical is what defines your region. We've defined this region. We know where the test statistic is. It's in the region of rejection. So we're going to reject the null hypothesis. So when I refer it back to here, we're going to reject the premise that mu is greater than the value, which means we're going to accept the premise. There's enough information provided that we can statistically claim that the mu from our survey of those 36 homes and Legacy Ranch, they are actually statistically using less water than the national average. So that is the conclusion, that Legacy Ranch uses less water than the average, which we're basically using the average reported by the American Water Association report. So this is the final conclusion of this problem. And let me just finalize by adding some format.